Welcome to this explainer. We're about to take a rapid-fire list of monumental scientific breakthroughs and turn it into one cohesive, absolutely awe-inspiring journey. We're going to travel from the mind-bending vastness of the cosmos all the way down to the microscopic elements that literally dictate our survival. It's an incredible story of human curiosity. And by visualizing these massive leaps in our understanding, we can truly appreciate the sheer scale of what we've figured out about our reality. To get us there, we'll be breaking this down into 4 parts. First up, our place in space. Then, the rules of reality. After that, the blueprint of life. And finally, conquering deadly diseases. Let's get right into it.
Section 1. Our place in space. Mapping the universe.
So, to really grasp the cosmos, we've got to start at the absolute beginning. An unfathomable 13.787 billion years ago, our universe sprang into existence. According to the widely accepted theory, an infinitely dense singularity just exploded. It was an event that literally created space, time, and absolutely everything within it. You know, our ability to even calculate that approximate age, which is largely thanks to the 1965 discovery of cosmic microwave background radiation, gave us our very first real map to understand the history of the cosmos.
Now, you'd probably think a theory that profound would have been named by its greatest champion, right? Well, actually, in 1949, on a BBC radio program, physicist Fred Hoyle coined the term Big Bang while actively trying to express his disagreement with it. He used the phrase to intentionally mock and insult the hypothesis. It's kind of hilarious when you think about it. History definitely has a wonderful sense of irony.
Okay, so once the universe existed, we still had to figure out our specific, honestly very minor place within it. And let me tell you, this was a massive struggle. For centuries, the ancient geocentric model completely dominated, stubbornly placing Earth right at the center of the solar system. It wasn't until the 16th century that astronomer Nicholas Copernicus presented heliocentrism as a mathematical model, proving once and for all that the Earth actually revolves around the sun. This Copernican revolution faced fierce protests from contemporaries in the Catholic Church, who desperately clung to the geocentric view. But eventually, the mathematical truth of our orbit won out.
That brings us to Section 2, the rules of reality. Understanding physics and matter.
The rules of reality as we knew them were forever rewritten by Albert Einstein. And it was all inspired by a 16-year-old Einstein just imagining himself chasing a beam of light. His resulting theory of relativity cleanly separates into 2 brilliant parts. On the left, we have special relativity, which tells us that the speed of light is a constant that just cannot be exceeded, giving us that famous E=mc² equation. Then on the right, general relativity adds gravity to the mix, explaining that gravity is actually a result of matter and energy curving space itself. Together, these 2 concepts prove that time is relative. It can literally stretch and squeeze. It completely transformed modern cosmology.
But here's the catch. Einstein's general relativity is really best for studying massive objects. When we zoom all the way down to study the absolute smallest scales of reality, we have to rely on quantum mechanics. Coined in the 1920s to fill in the blanks of classical physics, this field entirely embraces the counterintuitive. It deals with wild concepts like quantum entanglement, which involves what Einstein himself called spooky action at a distance, where subatomic particles remain inexplicably connected. I mean, it sounds like pure magic, but it is the actual bedrock of reality. It's the exact science that gives us modern marvels like lasers, transistors, and MRI machines today.
And speaking of the subatomic level, we really have to talk about how matter actually gets its mass. Enter the Higgs boson, often dramatically referred to as the God particle. Theorized in 1964 by Peter Higgs and his colleagues, it was likened to particles moving through an invisible molasses. It's the fundamental thing without which we and the rest of the universe simply could not exist. But theorizing it was one thing. Proving it took decades. It was only finally discovered in 2012, and it took CERN's massive 17-mile Large Hadron Collider to do it. That breakthrough fundamentally confirmed our deepest theories about the structure of matter.
Moving on to Section 3, the blueprint of life. How we got here and what we're made of.
The story of how we got here is this totally fascinating journey of gradual discovery. The idea actually dates all the way back to 500 BCE when the Greek philosopher Anaximander first suggested that humans evolved from other animals. But it wasn't until 1859 that Charles Darwin published On the Origin of Species. You see, Darwin had observed the remains of a giant animal similar to the modern sloth, and he realized these similarities weren't just some random coincidence, but actual evidence of natural selection. Soon after that, Thomas Henry Huxley explicitly linked humans and apes. And despite facing considerable opposition from some religious groups, ample evidence slowly built up into a rock-solid scientific consensus over the centuries.
Uncovering our genetic code, however, required a monumental, literally generations-long effort to map human DNA. It started with the initial isolation of DNA way back in 1869, leading up to the massive Human Genome Project launched in 1990. By 2003, we had 92% of it sequenced, and the final puzzle pieces were incredibly just completed in early 2022. This map of our biological blueprint has opened up some unbelievable doors for medical science. It allows us to identify disease-causing genes and even use cutting-edge tools like CRISPR to edit them for therapeutic purposes. It's a real game changer.
Which leads us perfectly into Section 4, Conquering Deadly Diseases, the microscopic battle for survival.
Now consider the shocking and honestly somewhat tragic story of Hungarian obstetrician Ignaz Semmelweis. Back in 1847, decades before the idea of microscopic germs replacing the old bad air miasma theory was accepted as fact, Semmelweis made a stunning discovery. He found that when medical practitioners literally just washed their hands, patient mortality dropped significantly. And yet, he faced immense skepticism. His peers literally jeered and mocked him for it. It wasn't until later microbiologists like Louis Pasteur proved that bacteria and viruses actually cause disease that Semmelweis was finally vindicated. Building on that realization that microscopic bacteria cause disease, we get one of history's absolute greatest happy accidents. In 1928, Scottish physician Alexander Fleming returned from holiday to find a strange mold growing in a petri dish of Streptococcus bacteria. He noticed the mold was secreting a substance that actively blocked the bacteria from growing. He named it penicillin, and just like Semmelweis, Fleming's contemporaries were totally unimpressed at first. But fast forward to World War II, and scientists at Oxford figured out how to mass produce it to cure bacterial infections on the battlefield. 200 million. That is the staggering scale of impact we are talking about here. Just to put that into perspective, that single accidental discovery in a forgotten petri dish completely paved the way for modern antibiotics. It is estimated that penicillin alone has saved 200 million lives. It completely changed the entire landscape of human survival.
Our final microscopic defense, and perhaps our most profound one, is vaccines. They operate on the principle of introducing harmless or weakened antigens to stimulate our immune system's antibodies. And the origins of this are fascinatingly ancient. It dates all the way back to late Imperial China's practice of variolation, which was a slightly gross but incredibly effective method of rubbing material from smallpox patients into scratched skin. This evolved over the centuries, eventually leading to English physician Edward Jenner creating the first official smallpox vaccine in 1796, and then later to 1930s breakthroughs where scientists learned to cultivate viruses in chicken eggs for mass production.
But, when we talk about introducing weakened antigens into our bodies, it's totally natural to have concerns. We absolutely have to ask the critical question that is so often raised regarding the immune response, especially nowadays when new medical technologies are developed so quickly. What if the vaccine makes them sick?
Well, to answer that directly based on the data, yes, our bodies do react, but common side effects are generally mild and only last a few days. This temporary minor reaction is a remarkably small trade-off to prevent the devastating, serious long-term impacts of deadly diseases. It's exactly this biological mechanism that has allowed vaccines to save countless millions of lives, essentially ensuring that many of us are even sitting here today to learn about it.
So, having traced our spectacular journey from the explosive birth of the 13.8 billion-year-old cosmos through the bending of space-time, the decoding of our evolutionary blueprints, and down to the microscopic germs we battle daily, we've really seen the sheer scale of human achievement. But science is never finished. So I'm going to leave you with one final, thrilling question to ponder. Now that we've mapped reality all the way from the stars down to our very DNA, what will be the next great discovery that changes absolutely everything? Thank you so much for exploring this explainer with me, and stay curious.